Okay, good morning, everyone. Thank you to the organizers, first of all, for inviting me and then also for putting me in this place in the program, because Kirsten's already introduced the model I'm going to talk about. Alberto has introduced the controversy I'm going to talk about, so I'm really in this sort of the ideal location in the program here. Obviously, I'm not going to resolve the controversy. I'm going to give you one particular angle on it, which has its limitations, but then can also teach us something. And if you're thinking it's the kind of fourth day of the meeting and it's raining outside, why don't I have a quick nap? I don't like theory anyway, which is a reasonable point of view to take if you wish. I've put some keywords on the right there which sort of connect to the general discussions. I'm going to talk about avalanches, rearrangements, criticality, and the related important concept, which is marginality. Okay? So the controversy you've already heard from. By the way, I should say this is work by Jack T. Parley, a very talented postdoc that was done locally. It's on the archive. It should appear shortly. So the basic problem is what happens if you take an amorphous solid, athermal, so in a regime where you can neglect thermal effects of the same type, so in the same class that Alberto has implicitly been talking about, and you start subjecting it to shear slowly. Okay? And then the simplest scenario you can have is what sort of Anael did in these kind of pioneering simulations in the early 2000s. You expect stress to rise gradually with strain and eventually to settle to some plateau value. This is, of course, an area where there's been lots and lots of work. I've put some review articles there if you want sort of more background. Many of them involve people in the room. So the question is, what happens? And people got sort of very excited about this, more excited than previously, I would say, from 2018, where sort of people around Ozawa and Berthier found that now that they could make very well annealed glasses, there was this characteristic change in behavior that Alberto has already alluded to, that depending on the degree of annealing, you can have either this kind of what they called brittle yielding, and that'll be my definition for the purposes of this talk as well. So a stress versus strain curve where you have a macroscopic stress drop, they call that brittle, and if you have some sort of continuous curve, then they call that ductile. Okay? And the interesting thing is that as you vary the preparation of the material, you can cross over between these two in a way that looks like a smooth transition. So you go from something that has a drop to something that has a smooth overshoot, and then eventually doesn't have an overshoot anymore. Okay? Whether these kinds of smooth overshoots should exist, that's in itself controversial, and you can ask Suzanne about that. She has lots more to say about that, which I don't want to preempt. Okay, so what you then see, for example, you see also that, of course, finite size sort of rounds this transition. You can look at stress variance as a signature of this transition. Okay, and one of the key sort of proposals in those original papers was that somehow this looks like what you see in a sort of well-known statistical physics model, which is the random field Ising model. If you drive that slowly, and I'll explain briefly how that works, you also see a transition like that. Okay? And so the question is, to what extent is that true? Okay, and again, there have been lots of sort of papers on that since then. So what we're going to try and do is basically use mean field theory to see what that says about the analogy to the random field Ising model or otherwise. So here's that comparison. Okay, so this is basically this is a sort of summary of what the simplest form of that mean field theory predicts. So it's basically a cartoon of what you see in the simulations. So R here is the measure of initial disorder. If R is greater than RC, you have a very disordered sample. You have this ductile yielding. If you have a well-annealed sample, where the initial disorder is below this critical value, you get this drop. Okay? So those are the kind of three regimes. There's a critical point in between here, which you do see in the mean field theories, and the analogy is with this random field Ising model, which is basically a bunch of ferromagnetically interacting spins, random fields acting on the spins, and then plus some field that you drive. Okay? And it's athermal, so the fields just flip when the appropriate local fields acts on them. And here
So this is the mean field theory of the random field Ising?
Yeah, when I say random field Ising model, I always mean the mean field version.
Of course,
there is also a finite dimensional.
That's what you guys argued.
And so here the disorder sits in the sort of random field distribution that these spins feel, okay? And then you find, similarly to what you see in these mechanical models, that depending on how disordered these local fields are, you either get what you'd expect from a sort of pure ferromagnet, you get an actual jump, right? But then if you have enough disorder, again, you get this kind of smooth transition, right? And so the idea was that given the qualitative similarity between these curves, I mean, except you can flip that one round, so the magnetization goes down from up to down, but otherwise this looks quantitatively very similar. So that was the sort of natural proposal at the time, okay? And then, of course, as you'd expect, if you, as I've already mentioned, if you change the system size, the transition becomes visible at large n. As you have smaller system sizes, it becomes smoother, and of course, it also becomes smoothed out if you start shearing at some finite rate. If you start shearing at a finite rate, you don't get a sharp drop anymore, but you get something that is smooth. You can see that here in this approach from large shear rate to small shear rate. Again, you've got stress versus strain there. And so we're going to look in the mean field setting at both of these approaches, the approach to the infinite system size and to the zero shear rate limit. Okay? Of course, in the simulations, and Alberto's talked about that already at some length, what you see when the drop happens is you see shear bands. Okay? Those are very pronounced for the big systems and the small shear rates, and then they become less pronounced as you increase either shear rate or you decrease system size. Okay, so that's the basic problem, is to understand what's going on there. We're going to do this using mean field theory. I'm not going to have to say much about that because Kirsten did a wonderful job of introducing the model that we're going to use, basically on a continuum of sort of going from the reality to something like particle-based simulations to lattice EPMs of the type Alberto was going to talk about. We're going to go one step further and basically throw out space, okay? And that will give us the mean field theory. That throws out at least some important physics, which is the shear banding, okay? But the idea is basically then to have something that's analytically tractable, where at least we can make some progress in understanding what these various singularities are. And so the model itself, I'll show it on the next slide, is just a model for the evolution of the local stress distribution. It's mesoscopic, exactly like Alberto's EPM. It's just based on local stresses, and the dynamics is very simple. You load elastically until you reach a local threshold, then you reset, and in the simplest case, you reset to stress zero. The details of the equation here aren't terribly important. This is the loading term. The key thing is really that you have this mechanical noise. So the assumption in this model is that whenever there's a yield, you have a perturbation of all the stresses in the system. And this is modeled here in a very simple diffusive way. So you effectively have Gaussian noise acting on all the stresses in the material. That's a simplification. I'll come back at the end at how this can be improved based on sort of work that Mathieu has done. Okay, so this Y will come up several times. It's just the yield rate in the system, and the assumption is that the mechanical noise is proportional to that yield rate. At the moment, we're not looking at disorder. Again, I'll come back to that. This is kind of the vanilla model. Okay, so we're going to basically, at the end, as I've already said, I'll come back to this point of how to improve the noise, which if you do a better job of modeling, it has power law statistics. And then in the talk, I'm going to first look at the approach to the small shear rate limit for infinite systems, where we can use this master equation, and then I'll look at the finite size effects in the quasistatic limit. And the idea there is I will leave out most of the sort of details of the derivations. Here, what we do is basically is an expansion for small shear rates of the master equation, which involves some sort of boundary layer scaling. And in this part, mainly we're going to use a mapping of the avalanche dynamics to a random walk problem that Jagler introduced, and then some general scaling arguments. Okay, so let's first look at the baseline. That's the sort of what this model predicts when shear rate goes to zero and you have infinite system size, so you can work directly with the master equation. Okay, so these are the sorts of results you get if you basically solve the equations numerically. So what you have here is one of these disordered samples where you have, in the limit of small shear rates, a jump. And of course, then as you have higher shear rates, you get a smooth curve of stress, sigma versus strain, gamma. I'm going to use capital sigma here to distinguish from the local stresses, which are the small sigma. And Mathieu already showed with Marko Popovic in 2018 kind of how to understand the behavior, at least up to this yield point. You can do that in a sort of clever way by basically avoiding this avalanche that happens there, which I'm going to call the infinite avalanche, because it affects an infinite number of sites when the system is infinitely large, just to distinguish it from all the other avalanches that will happen elsewhere. So the one drop is, I'll call that the infinite avalanche. And then from the fact that this solution is smooth, you actually get that the exponents of that characterize the singularities, in particular what happens around the critical disorder and what happens on the approach to these drops, they have the usual Landau form. So on the approach to the drop, you have a square root singularity, that's this exponent beta equals a half. And round here, you have an exponent 1/3, that's this delta equals 3. Okay? And this just comes from the fact that these curves are basically smooth. So this one looks like a cubic form, and this one, if you look at this, the dashed curve here it's parabolic, so it gives you this Landau exponent. And so at that level, really, the random field Ising model and the mean field model for the yielding are exactly the same. So one can ask one first question on the approach to kind of the small shear rate limit is what actually happens in this avalanche. So what happens in this big drop of stress? Okay? And it turns out you can basically resolve this avalanche, which is like a first order phase transition. So it's like doing, in some sense, finite size scaling analysis on first order phase transitions. And what you find is that these avalanches have a universal shape. If you look at the yield rate against some scaled difference in strain, if you look at this for 10 seconds, you realize this is actually just time. Okay? So it turns out the way the avalanche proceeds in terms of plastic activity against time is universal, and it always has these tails here, which are power laws, and they scale as 1 / time squared. Okay? And interestingly, that's related to something that we saw before in systems that aren't actually strained. They're just aged from some initial condition, right? And the reason is that why this happens here is because you're straining the system very, very slowly. So it reaches the point where it has the avalanche. Once it's got to that point of high plastic activity, it basically doesn't know that you're straining it, right? And so therefore, it essentially just ages. Okay, so there's an interesting connection there between the dynamics in this kind of driven experiment and what you actually see if you take basically a Pauli anneal sample and you let it age. You get exactly the same exponents. That's kind of one of the first insights. We can also look at the approach to this point, and what the mean field theory predicts is that you basically get this spinodal. So you have this square root here in the plastic activity. So as the stress here curves down, the plastic activity increases. So you get this parallel half, which is the spinodal, and it turns out in the infant avalanche, then you cross over to this exponent of 2, which I just mentioned. Okay. That describes how the mean field theory, kind of what that predicts for how you get to this catastrophe where the material yields. Right? So you have this combination of these two exponents. You can also look at how the maximum in the stress shifts with the shear rate. So here are high shear rates, here are low shear rates. Okay. So what you see as you shear more quickly, of course, you get more of a maximum. So the maximum shifts to the right and up. Right? And actually, we can work out what the power law of this is. So the strain here at which you yield basically shifts as a square root of shear rate. Okay, so that's a sort of prediction. So the faster you shear, the later you yield. And if you look at the simulations here, that looks sort of qualitatively similar. So that's also an aspect that's reasonable. Yeah. That's a good question, which I've temporarily forgotten, and I should know this. I think it does. Ask me over coffee, and I'll have checked by then, I think. It does, yeah, I think. If anyone else wants to correct me, then say. Yes. Okay. I can't remember when I started. How much time have I got notionally? Great. Okay. Right, so let's look at this, the second part. So now we're going to look at quasistatic shear, and we're going to look at finite systems. Okay. So the key thing that we want to look at in these finite systems is the avalanches. Okay. Why do we get avalanches? Well, because basically once you have a rearrangement, then the way this model is constructed, it triggers further rearrangements. Those are the so-called avalanches. In the quasi-static limit, these are perfectly well defined because I just strain, I trigger the avalanche, I wait for it to proceed, and then I strain again. Okay. So I don't have any problem with delimiting the avalanches. Okay. And the avalanches in this model are very simply related to the stress drop, because if I just set the local yield stress to 1, then basically the stress drop is just the avalanche size S divided by N, right? Because stress is just average. Okay, so I get things that in steady state look something like this. This is for increasing system sizes, just stress versus strain in steady state. You see that there are large fluctuations, and they decrease as you increase the system size. And if you can interpret that as saying, well, there's some, so the avalanches have some sort of fractal dimension. They're not finite-sized. They're also not extensive, but they have an extent which has scales as some interesting power with the linear scale of the length, or in the mean field context, you then want to express that as basically system size to the power of fractal dimension divided by spatial dimension. Okay. So there you already see one interesting difference to the random field Ising model, because that has finite avalanches, always, certainly in steady state. So that has a fractal dimension of 0. So that's already different, okay? And in the amorphous solids, basically what the fact that these avalanches are growing with system size tells you that these are in some sense marginal. They're always poised at the edge of an avalanche. Okay? And that would be one of the key differences to the random field Ising model case. Okay. So when we now look at these avalanche size distributions, we can take this random walk mapping by Jagler, and we can work out a very accurate prediction for what this avalanche size distribution is. And here's the form. Okay, so you end up having a power law with some avalanche size exponent tau, and then you have a cutoff which has a linear plus quadratic exponential form. So it's basically a shifted Gaussian. And the scale of this cutoff is system size to the power half. Okay, so these are these kind of fractal avalanches. That's a fractal dimension, which is half the space dimension. You want to interpret it that way. And not unexpectedly, these avalanches are basically proportional to the rate of plastic activity, which is this y. The y tilde is plastic activity divided by shear rate. That's the sort of interesting limiting quantity. And it's also related to basically the steepness of the stress decay. This chi is just that derivative of stress versus strain. As you'd expect, the more quickly you relax stress or the more plastic activity you have, the bigger the avalanches. And they have this fractal scaling with system size. They grow in size as n to the power half. Okay? And then we can take this, the model, and simulate it on a computer to check that prediction. And it turns out both in the steady state, but also, for example, in the transient. So if you look at a ductile sample, which at its peak, where it's kind of most plastic, right, we can just take all of that data, we can look at the avalanche size distributions, and then if we scale them in the predicted way, then they all collapse onto a sort of master curve. Okay, so that prediction works very well. The interesting thing is this exponent tau, and it doesn't have the mean field value, which would be 3/2, which you get out of the standard sort of mean field theories. Actually, it turns out that it's very close to 1. And that's true, as I said here, both whether you're in steady state or whether you're in a transient. Okay? And that's sort of quite interesting. And it comes from the fact that kind of in this random walk mapping, you sort of end up being in a marginal case. This exponent is not universal. It's actually determined by material parameters. In principle, could be between 1 and 3/2, the mean field limit. But it turns out that kind of in this model, at least the parameters are typically such that you end up being very, very close to 1. It's a non-universal avalanche size exponent, which, because of the sort of properties of these models, numerically works out to be very, very close to 1. Yeah?
Looking at the curve, it's not 1, because it's I don't know, on the right-hand side, it looks like there is, it departs. So how different from what would it be? I mean, if you were fitting more the actual data you have. I mean, is it 1 point, no, it's smaller, so is it 0.9, 0.8?
Obviously, you also have an effect of this cutoff, right, which has a negative term there and a positive term there.
Yeah, I don't know.
So in the fits, I can look up the numbers in the paper. They are kind of, I think, of the order of 1.05 or something. Pretty close to 1. Obviously, you can't have exactly 1 because otherwise you have a problem at the lower end. Right? But I mean, so the experiment is not universal anyway. Right? So it's not worth worrying about it too much, probably. The interesting thing is that it does end up being very close to 1, even though in principle it could go up to the mean field value. Okay. Then let's look at the rounding that I already showed you, and now we're looking at the brittle regime here. So here we have kind of average stress versus strain curves, and the thinner lines are individual samples. Okay? So there's individual runs of. And so that's a sort of zoom in here of the region around the yield. Obviously, here you see the fluctuations aren't all that big, right? They all macroscopically look the same, but if you look closely, then You see that there are distinct fluctuations where distinct yields, right? And you can sort of see that the fact that the macroscopic average response is a smooth curve basically comes from the fact that you have fluctuations in the yield strain. That's the sort of main physical effect. Okay. The same thing, by the way, also happens in the random field Ising model. Right. Again, you have sort of that's the sort of zoomed out version. Then, if you look closely, you see again that there are fluctuations. One thing that's interesting that you already notice here, that's qualitatively different without even doing any analysis, is you see here is the n infinity infinite system size yield. And you see the finite samples always yield later. We don't have any proof of this, but certainly we don't see any that yield before. Whereas in the random field Ising model, you can yield earlier or later. And if you think about it, that actually makes sense, because the random field Ising model, because it's ferromagnetic, if you accidentally have a local event that's in some sense too early, the only thing it'll do is it'll provide for more events later on, and so therefore you can actually have a transition before the one in the thermodynamic limit, whereas in the yielding case, because you have these plus-minus propagators, right? Even if you have a random fluctuations, it does not necessarily give you more plastic activity necessarily. Okay. So you can do this quantitatively. You can look at the yield strain fluctuations themselves, and then you can just predict, as a sort of simplest approximation, that the average stress versus strain in that transition region is just the probability of having a yield strain in the right place times the average stress drop. And if you do that, you have two sets of curves there. They actually overlap very well. So one of them is the actual slope of the stress versus strain curve. The other one is the prediction from the yield strain variation. And we find that the scaling of that yield stress, of the yield strain fluctuation is again as n to the minus a half. So the bigger you make the system, the smaller these fluctuations get. Interestingly, that also actually matches with 3D simulations. These are ones by Prokachev in 2017, and they find the same exponent. Okay, so even though this is mean field theory, that exponent in d equals 3 is quite similar. The 2D exponent is actually smaller. It's around 0.3. There's a data by Ozawa. Okay. So that's the sort of the view of that rounding transition. And here is the sort of quantitative comparison between the random field Ising model and the Hébraud-Lequeux. So what you see here, again, is that these yield strains are all to the right of the infinite system size line. That's what I showed you earlier. Whereas in the random field Ising model, they're almost centered around this limit here. In fact, if we do a sort of numerical scaling analysis, it looks like the mean of this distribution has a bigger correction from 0 than the standard deviation. So it looks like actually in the limit, you would really stay kind of well away from the infinite system size limits. But the exponents are not very different. One of them is 0.5, the other one's about 0.4. But that sort of is sensible given what I said about the qualitative difference between the models earlier. Okay. And we can also look at the fluctuations of the maximum stress drop. So we basically take each individual run, we look at where it fails, so that's the maximum stress drop during the trajectory, and then we look at the statistics of that. That's been used before as an order parameter kind of to detect this ductile to brittle transition. So first of all, if you look at the average value of the stress drop, then here for the samples with low disorder, so the well-annealed ones, it's finite. So you have a brittle transition. Here's the ductile regime where this average depends again on system size, but goes to 0 as the system goes to infinity, the system size. And then here are the data for finite n. And you can scale this again, and we can derive the exponent. So this scales like n to the power 1/3, which is sort of related to the Landau exponent basically at the transition. Okay? And there's one interesting thing we can do is we can actually take data for these peak fluctuations from 3D simulations, and we can just put them on the same graph. So here's the peak height of this of the fluctuations. I should have said this earlier. Sorry, this is the variance of the stress drops, and that was the mean. What I was plotting here is the variance. And if you plot those kind of on the same graph, they look like they're basically on the same line. Okay, so that's kind of interesting that the mean field model quantitatively matches what you see in the 3D simulations there. Okay. And then finally, there's this interesting question of precursors to to a brittle failure, which Alberto already mentioned. Okay, so I would call those kind of spinodal avalanches because it's the approach to the brittle failure. Okay, so what I've plotted here is average avalanche size as a function of strain for brittle samples, scaled by the typical scaling that we looked at earlier, the fractal scaling. Okay, so these are already large, okay, and they already grow with system size. So that's kind of my marginal baseline in some sense. And then what you see is that on top of that, you have, as the system size grows, you have avalanches that become bigger and bigger as you approach the spinodal. So certainly within the mean field model, there's good evidence that these spinodal avalanches exist. I should say that the way we measure these is we basically condition on the sample not having failed, because of course, otherwise the measurement doesn't make any sense. So we run systems up to some strain, we take all the ones that haven't failed, and then we look at the average avalanche size. Yeah?
You're fixing, when you measure avalanches, are you fixing the stress or strain?
Strain. Yeah, this is all strain control. Okay. And then you can look at basically the height of this peak above that one, okay? And you find that in the RFIM, this goes like n to the power one quarter. This is the corresponding random field Ising model plot, okay? But interestingly here, I've not scaled by this fractal size, right? Because as I told you earlier, in the random field Ising model, the avalanche is actually finite, okay? And then they diverge here at the spinodal. Interestingly, that exponent numerically looks very similar in yielding and in the random field Ising model, right? But it has a different meaning because here we have, in the yield, we have basically the spinodal singularities on top of what's already large avalanches from the marginality. Okay, and in fact, we can compare this to simulations. So what we did here was we basically took stress drop data from sort of the original 2018 paper. We converted these stress drops into avalanche sizes, and then we looked at the statistics, okay? So here what we've done is we've normalized the avalanche sizes by the appropriate measured fractal dimension. And then again, what you see is that as the system size gets bigger, this divergence of the relative avalanche size, if you want, is earlier, and it gets bigger as the system size gets bigger, okay? But obviously, we don't have enough data there to really say, okay, let's start looking at exponents. But certainly from that sort of data analysis, it looks like the qualitative trends you see in the avalanches in the 3D simulations are actually also quite similar to what happens in the mean field model. Okay, so then finally, an outlook to power law noise. So bring all that on one screen. So I've actually forgot to put the citation to Mathieu's paper there, sorry. So this was a paper by Lin and VR, where they sort of argue that, okay, what you should really do to have the sort of proper description of the mechanical noise is, rather than pretending that the stress kicks that you get everywhere are Gaussian, which is effectively what Hébraud-Lequeux does, you should really be taking something like an Eshelby propagator, which you've seen many times before in this talk, which has a sort of power law dependence on distance from your plastic event. And then the way to construct a mean field theory is you basically ignore the sort of spatial correlations, so you just look at the statistics of these propagator elements, okay? And you get a power law for these stress changes with an exponent that in the kind of realistic case, where this decays radius to the power minus spatial dimensions, is just 1. We keep this mu sometimes because it turns out as you go from mu equals 1 to 2, you basically go back to the Hébraud-Lequeux limit. So this is kind of often a useful parameter, okay? And that's just a sketch of the noise distributions. That's the Hébraud-Lequeux Gaussian, that's the power law. Here they're scaled, so they have the same variance, so you can sort of see the difference. Intuitively, the effects out here are basically that's when your neighbor yields, okay, as a mean field representation. Those are the kind of near field effects. Those are the many, many very small stress changes that the elements feel, which are very far away. Okay, so basically what we can do, we don't have any analytical predictions for what that model does in terms of avalanche statistics, but we can simulate it relatively straightforwardly. And what you find is actually that you get quite similar distributions, but the exponents now look different. What we get for mu equals 1, depending on how we measure the exponents, we get something around 1.3, 1.4, which actually is, again, lies quite well in the sort of ballpark of what you see both experimentally, for example, in ductile metallic glasses, and in lattice EPMs, which you can do in sort of 2 or 3 dimensions. Typically, the match is better in 3 dimensions. And actually, in that, you can also then quantitatively fit the distributions with the same form that we had earlier. Okay. So that's certainly suggestive that if we find better ways of understanding this kind of improved mean field model with the power law noise, we should get even closer to the real world in some sense. Of course, modulo shear bands, which, as I said from the beginning, are not in this theory. There are possible ways of getting around that in the mean field context, but they're certainly not in the models as written at the moment. Okay, let me summarize there. So we've looked at this kind of mean field theory and how it behaves in these around these limits of infinite system size and 0 shear rate. Okay, so in the first part, I've shown you briefly that the way the macroscopic failure works, the time dependence of that avalanche has some universal features. And something I haven't actually told you about, but I'll mention briefly now at the end, we can also look at the peak susceptibility. So that's, again, the largest slope of stress versus strain. And we can look at how that depends on shear rate at the critical disorder. Okay, and we have an exponent prediction for that, which is shear rate to the power minus a fifth. And that's in principle something that one could try and tease out of simulations if one kind of can get around the finite size effects. Then the second part, I told you about these avalanche exponents, which are close to 1. So they're effectively universal in that sense, although they're not universal in a strict sense. They're just kind of numerically universal. And that works both in the steady state and the transients. We do get Landau exponents basically because of simple smoothness arguments. Again, something I have not told you about is that there are interesting signatures of the singularities in the stress distributions, basically to do with the shape around the yield threshold. And then one of the key differences to the random field Ising model is that when we have either criticality at the critical disorder or generally the spinodal effects before the onset of the infinite avalanches, these happen on top of these marginality features of the avalanches. So we have avalanches which are already large. They always have these fractal dimensions, and then they get even larger as we approach the catastrophe. Okay. So there's lots of things one could do. Sort of even within this framework, it would certainly be worth looking more at the models with the power law mechanical noise. There's interesting questions in terms of what happens with this so-called pseudo gap exponent as you cross the kind of brittle failure. I think the question of exactly what is the universality class of this transition remains open. I think it's clear from what we've done, it's not the random field Ising model. Okay. There has been a nice paper on sort of testing the effects of the propagator in the random field Ising model. So you just replace ferromagnetic interactions by Eshelby. That gets a lot of the features right that kind of resemble what we see in the yielding. But interestingly, the avalanches stay finite. Okay, and there's sort of an interesting question of why that is. One conjecture could be that it's really to do with discreteness. So you have discrete degrees of freedom, so you have spins, and that really makes a difference. Right? So that's one possible explanation for why that doesn't seem to be still quite the right sort of description. Okay, and Kirsten's already told you about other effects in the propagator, that this was an approach in steady state to 0 shear rate, but that's definitely also an interesting avenue to pursue what the exact details of the propagator do there. As Sri's already mentioned, one ought to extend these models to local heterogeneity in the yield thresholds. I mean, those models kind of have been written down, and we think that's probably necessary if you want to have a unified description of what happens under uniform shear, as I've just discussed, and under oscillatory shear, as Alberto discussed before me. Okay? You can then, once you have this kind of description, you could think about better ways of modeling the initial preparation. In principle, you can feed in, for example, yield stress measurements from sort of frozen matrix measurements. If you don't know what that is, ask me afterwards. I think one other interesting question is the role of geometry, which we don't, I know, certainly for simulations, we tend to just start with the simplest geometry with shear. And if you look at actual sort of metallic glass failure, of course, it doesn't look anything like a sort of simple geometrically sheared box. And I think there are interesting questions there in both directions. So in some sense, there's certainly evidence that fracture under tensile stresses is well described by things like fiber bundle models, which have ferromagnetic interactions, so they're much more like the random field Ising model. On the other hand, if you look at cavitation, there's nice papers involving Pinaki there, then you see, for example, as the first event, something that clearly looks like Eshelby. Right? So even in something like cavitation, where you have basically a sort of something that's not a shear geometry, right? You still have effects which have this the propagator in them. So you might expect marginal effects even in geometries like that. So I think there's a very interesting question there to delimit exactly when these kind of quadrupolar effects are basically relevant in which geometries. And then there's many other things we can do. We've looked recently at fatigue failure under oscillatory shear, and you can ask me about that. And then, of course, linking finally to the active systems, and Mathieu has mentioned this earlier, we could also, one of the things that we're currently thinking about is how to describe yielding by local active forces within the same setup. Of course, we could also include thermal effects. That's partly already been done in work by Giulio Berardi. So there's lots of other axes that one could go into, but there's coffee, so I'll stop there. Thank you.